We are now? Okay. Well, thanks, guys. Nice to see everyone again. My last two lectures are going to be about some small application, perhaps, of this liquid formalism that Peter was talking about. But I maybe want to start, I want to, in some sense, pick off where Peter left off. So Peter's last lecture, he defined this, well, you have to fix a parameter p between 0 and 1, and then you get this liquid p subset of condensed R modules. It's an abelian category with nice tensor structure. I don't know if we have the best possible notation for this. Compact projectives, enough compact projectives given by these spaces of measures. And if you recall, the way it was defined was, well, we started with a more naive space of measures, which is the usual Redon measures, which are the ones that kind of pop up in classical functional analysis. But then we saw that if you tried to take those as your basic objects, then you wouldn't be generating an abelian category. At least, yeah, I mean, you could generate an abelian category, but it wouldn't have any nice properties. So this list of axioms that I gave when I was discussing the solid theory would fail. And so we had to shrink this space of Redon measures, replacing basically the one summability condition, which is implicit in the notion of a Redon measure, with this more stringent condition of p summability for p less than 1. And then we took a union over p prime less than some fixed p. But then the question, I mean, and Peter even mentioned that this kind of drastically changes the kind of measures you're allowed. So if you look on the base point, then in fact you only get countable sums of Dirac measures. So evaluated on a point, just the underlying real vector space here, you only got countable sums of Dirac measures. So you're actually somehow getting, well, you're getting closer and closer to the uncompleted theory where the free things were just the finite sums of Dirac measures. So a question you have to answer is this complete enough? Are liquid modules complete enough? And to test this, you have to try to calculate some completed tensor products. So we take some of our favorite, by the way, M-complete. Peter also talked about this notion of M-complete, which is a quasi-separated thing. So it was kind of the analog of liquid if P is equal to 1. Well, this is contained in P liquid for all P. So you can always take any N-complete thing, in particular any complete locally convex topological vector space, you can view it in there. And the question we'd like to address in the beginning here is, how is the new liquid tensor product related to some more classical tensor products that you might consider on locally convex vector spaces? So, well, the first example, if V and W are Banach spaces, well, and then you could take the liquid P tensor product. This is not a Banach space. It's not even locally convex. Liquid category, yes, is closed under colimits and condensed. It's closed under limits and colimits. That follows from the axiomatics. Yeah, so this P liquid tensor product, it only, yeah. We're kind of only adding in P summable linear combinations of elements in V and elements in W. So there's no guarantee that you can define some sort of Banach norm on this. Or well, I mean, I guess, yeah. It's just not a Banach space if you take a close look at it. It's less complete then the least complete of the Banach-space tensor products, which is the projective tensor product, which would be more similar to the liquid one tensor product, or in fact, as Peter explained, it is the tensor product of the M-complete things in this condensed world. So that's not good, and it doesn't. And also, same if V and W are Smith spaces. So these classical kind of L1 Smith spaces, the dual to Banach space, they're also not closed under this liquid tensor product, and their tensor product is some non-locally convex thing. So that
this tensor product of Banach, I don't think we even know that this is in degree 0. I think this derived tensor product would still all over the place. But I guess you're talking about the abelian level here, anyways. But
yeah, that's an interesting point. So you're saying that.
I don't think there's any reason that it would have to sit in degree 0.
Right, that's an interesting point. Yeah, I hadn't considered that, but you're right. Yeah, I agree. Okay. Right. So that's yeah. So by the way, what do we know? Before I get to, so this looks pretty bad, but what do we know? Well, we know by definition. So if you take these spaces of measures on, well, yeah, extremely disconnected, but in fact, it also works for profinite. So everything that Peter proved in the previous lecture, verifying these axioms for these compact projective generators, actually he never used that they were extremely disconnected. So everything worked just fine for a profinite set. And what that ends up telling you is that the value on the free thing on a profinite set is just given by the same formula as the free thing on an extremely disconnected. And all the properties work just fine.
It's less than P not greater than P, by the way.
Oh, sorry. Yes. I always get, because of this greater than R in the, yeah, thanks. I always get confused, or I think my hand does at least. Right, so this is the same thing as M less than P S cross T. And actually there's a nice special case to consider, which is not extremely disconnected. It's this familiar sequence space with a limit point added. So it's the initial convergent sequence, so to speak. So then, yeah, and in fact, so note that this measure space, oh yeah, no, maybe I want to make it, I don't know, well, I want to make a remark just at the beginning. So we just saw in Peter's lecture that to prove the existence of this liquid theory over the reals, we have to deform the reals to this arithmetic Laurent series ring in one variable over the integers with convergence condition. But now that we have the liquid theory over the reals, we're not going to need to do that anymore. So for everything that I'm going to talk about, the applications to complex analysis and so on, we can just stick with the real numbers and the liquid theory of the real numbers. We don't need to deform to anything arithmetic. So we'll just, that for us is just an input into the proof of the existence of the liquid theory over the reals. Okay, I just wanted to make sure with that there. Okay. So this contains R as a summand because, well, maybe I'll write N union infinity. So this measure space is functorial, so this maps to measures on a point, which is the real numbers, but then you can also include the infinity. So that makes a summand. So we can take what is it called? The complementary summand will denote L less than P. I don't know. Yeah. Smith, I guess. So it's the Smith space less than P analog. Well, I guess less than P Smith space analog of usual sequence space. So it is, well, yeah, it's just the set of all lambda n with n in n such that the sum of the absolute value of lambda n to the p prime is less than infinity for some p prime less than p. And it's given that, well, I guess not quite Smith space, but so it's a union over p prime of p prime Smith spaces. So where what you would think should be the closed unit ball for this norm will actually be a compact Hausdorff space. And it's actually similar to what Tomer remarked. It's actually just the same thing as giving this the condensed structure coming from viewing it as a subset of r to the n and making the obvious analog of this for s-valued points. Right, it's also sort of by the construction here, it's also the free liquid P vector space. On a null convergent sequence. So giving so to speak, yeah? So giving a convergent sequence in a liquid vector space is the same as giving a map from this S here, a convergent sequence plus a limit point, I should say, since remember, it's not necessarily Hausdorff. And then we've decided, when we mod out by this inclusion here, then we've decided that the limit point should be 0. Right. Yeah, so that's a nice example to take. It's related to familiar sequence spaces. And when you do this tensor product of these two things, yeah, you just get the analogous thing with n cross n instead of n. Right. So now I want to explain. Now I want to recall an idea of Grothendieck. In functional analysis. So the real numbers are more complicated than the p-adic numbers. And we've already seen this in setting up this liquid theory because we have this parameter p that we have to keep track of. And we had p between 0 and 1. And classically, you also let p be bigger than 1. And that's an important scale, so to speak, in functional analysis, this scale from L1 to L infinity. You know, if you do duality, it flips the scale and there are all sorts of things like this. And this is responsible for a lot of subtleties in functional analysis. The fact that there are different basic shapes you can have for compact convex figures. Like this is L infinity, this is L1, and then there's this beautiful L2 theory, which somehow plays a big role classically because it's self-dual, but doesn't play much of a role for us for some reason. And then we have these things like L1 half here. So there are all sorts of different shapes of compact convex figures, which is different from in p-adic functional analysis when everything's just a box, basically. It's just a ZP module, a compact ZP module. And that's because of the ultrametric property, right? That bounding a bunch of p-adic terms by some fixed bound is the same as bounding all of their partial sums by that same bound. So there's no difference between this and this. But so Grothendieck figured out a way to make all these subtleties disappear, or figured out a setting in which all of the subtleties get completely wiped out. So these subtleties are wiped out in the nuclear context. So, so let me recall. There is a notion of trace class, or I guess you could also say a summable. Maybe the term is one summable. Maps of Banach spaces. V to W. And you can define it as maps coming from the V dual tensor W with a projective tensor product. But there's let me give it actually this most basic example is you take the sequence space L1 and you map it to itself by some by a diagonal matrix. So just scalar multiplication in each entry, where this is also one summable. So that's the basic example of a trace class map between Banach spaces. And in fact, this is in some sense the only example. So any trace class map between any two Banach spaces factors through one of these. So with lambda n as above. So you kind of only need to look at this one example to get the idea of what's going on with trace class map. Huh?
Don't you have to take one of them to be L infinity?
I
think the basic example should be L infinity going to L1 via lambda ends, no? I'm not sure.
Right, you're right. Yeah, I'm sorry. Yes, thank you. Absolutely. Yeah, certainly. Yeah. Thank you for catching that. Okay, so you basically only need to look at this one class of maps in order to understand this one kind of, this diagonal map in order to understand what a trace class map is. Where was I going with this? Right. So then you can note you can note the following. So I want to explain why the notion of trace class map obliterates a lot of subtleties. And the first remark is one subtlety which I didn't bring up here, but which was already in place in the p-adic discussion, was there's a difference between Banach spaces and Smith spaces. So not only do you have the choice of what your basic objects can look like, in the infinite dimensional setting, you can decide whether these should be open balls like in Banach spaces or whether they should be compact Hausdorff spaces like in Smith spaces. But this distinction is going to get obliterated here. So we have the Banach space version of L infinity and the Banach space version of L1. And in fact, and these Banach space versions map to their Smith space versions. And any such map like this with the lambda ends, it actually factors through the Smith space version. So in other words, it's a continuous map, not just on the Banach space level, but also on the Smith space level. And then, of course, if you wanted, you could go over to the Smith space version here too. Now, why is this? Well, basically, what does it mean that you have what does it mean that a map should extend over the Smith space version? Well, the obstruction to extending is, in general, the fact that if you take the closed unit ball in the Banach space, it doesn't map to something compact here. But this is a basic feature of a trace class map, that it is compact. So that the closed unit ball does map to something compact, and that's what makes the Smith space. But you can sort of see it more explicitly as well. So what is the image of this thing? It's the collection of sequences in L1, which are L1 for some uniform reason. Yeah, so there's a fixed L1 sequence such that which bounds all of the things in your subset. So they're L1 for that because they're all term-wise less than or equal to that fixed sequence, right? And that's the kind of thing that distinguishes closed unit ball. That's exactly the kind of thing that is compact in a Banach space, is if you ask for a uniform reason for the norm to be bounded, not just the norm being bounded itself. So that's, I don't necessarily want to get into exactly how that works, but it's not too difficult to see. But then the other thing, and then that's a remark one. So that's one subtlety obliterated. Well, I haven't said exactly how, but a second remark is that, so I said there's this notion of a one summable map or a trace class map between Banach spaces, but you could also view your Banach spaces as being like, p Banach spaces for p less than 1 or something like this. Or you could work in the Hilbert space context, sort of in two Banach spaces with an analogous discussion. And then you'd have the notion of a two summable map of Banach spaces. Or you could just, basically just put an exponent here, whatever you like, for the summability. Any p summable map is automatically p prime summable for, what is it, p prime bigger than p. And also, if you take the composite of two p summable maps, it's yeah. So there's this Holder inequality that. Well, I'll just do it in this special case where I remember the answer. It's a 1/2 summable. So one summable will imply two summable, and if you have composite of two one summable maps, it's 1/2 summable. So you see, if you have finitely many composites, if you have enough composites of trace class maps, you can move between p and q summable for any p and q in the whole scale from 0 to infinity. Commensurable after only finite steps, finite composites. And we already saw, I guess Peter made this, yeah, I sort of phrased it wrong. I started with the L1 space. I was really supposed to start with L infinity. But another thing, if you do restrict to L1, then you also get to put an L1/2 here. So you can also, on the level of the spaces, all these maps factor through other LP spaces with P maybe close enough to the P you started with. So both on the level of the spaces and on the level of the maps, the P doesn't matter. And anyway, so the definition that Grothendieck made was, so a dual nuclear Fauché space, abbreviated DNF space, is a topological vector space. Well, we'll work in the condensed context. It's equivalent to whatever topological definition you make. Is a filtered union of Banach spaces along trace class injections. And then dually, a nuclear Fauché space.
Countable?
Huh? Oh, sorry, thank you, sequential, yeah, sorry. Yeah, thanks. A nuclear Fauché space is a countable inverse limit of Banach spaces. Along trace class, along, dense trace class maps. And then the above discussion, if you are Banach spaces separable here? It actually ends up not mattering, Scholze. So there's this fact with any trace class map of Banach spaces factors through one of these examples here, L infinity L1, and those ones are separable. So basically, there's, yeah. I mean, the key point there is that I won't get into it. So the above discussion means you get the same class of spaces. If you take, you do the analogous thing in P Banach for any P. Yeah. So yeah, that's this obliteration phenomenon. So yeah, that's a classical story. And yeah, so then the claim I would make, which essentially follows from that analysis, so you switch to the LP version and then the Smith space version, and then you take the union over P less than some fixed P prime. So if V is a dual nuclear for V and W are dual nuclear Fauché spaces, then you can check that the liquid tensor product is the same as the usual completed tensor product of Grothendieck. And this is why Grothendieck invented this nuclear concept. There's a million different completed tensor products for Banach spaces, but they're a natural extension to nuclear spaces are all the same. So this is kind of independent of any choices. So it makes sense that it would also be the same as the thing we defined. And you prove this by writing, using these ideas to write V and W as filtered unions of these sequential Smith spaces instead. And then you can just do the calculation by hand and see that it gives the correct guy. So use these basic Smith spaces here. And I'll make a remark that the same is true for nuclear Fauché spaces, but this is much harder to see. So I mean, already in my lecture on p-adic functional analysis, I proved the analog of this claim there. So there's the difference that every Banach space is nuclear. But anyway, so then it was every Fauché space that counts as a nuclear Fauché space. But then even there, it was quite difficult it took a lot of work and analysis to check that the solid tensor product of two Fauché spaces was the projective tensor product. And here you can use similar tricks, but it's just, it's not as algebraic. There's epsilons and stuff. And so it's, it's not as easy to see. But in fact, I'm going to avoid using in the discussion of complex analysis, I'm going to try to avoid using nuclear Fauché spaces as much as possible and stick with the dual nuclear Fauché spaces, which are kind of amenable to calculation by hand, just because it's a filtered union over a countable subset of Smith spaces, which you can control. Okay, so let me do an example there. So this is rings of holomorphic functions. And you can of course handle holomorphic functions in several variables. But I'll just for both of these lectures, I'll stick to the case of one variable and Riemann surfaces, just for simplicity. So let's write d bar for the closed unit disk. In the complex plane. I should say, so now I'm about to do complex analysis. So when Peter was talking about liquid vector spaces, it was always liquid real vector spaces, right? Now I'll be working in liquid complex vector spaces, but you can just define those as C modules in liquid real vector spaces. It's just a algebraic base change. There's nothing happening there, so. But from now on, all my liquid tensor products will be implicitly over the complex numbers, not over the real numbers. Okay, just add some extra copy, or cuts down the. Right, and then we'll write O d hat for the ring of holomorphic functions on the closed unit disk, which is the functions holomorphic on an open neighborhood of d hat, which may as well be a disk of slightly larger radius. So these are also, I guess, in the p-adic setting, these are also called over-convergent functions, but it's also just the standard definition of holomorphic functions on compact subset of the complex plane. This is a dual nuclear Fauché space. So what's the basic reason behind that? Well, like I just said, it's the union of functions holomorphic on a neighborhood of d hat. So we can write this as the union over all n, or I don't know, or epsilon greater than 0. I can take epsilon equals 1 over n for a countable collection. So of the open unit disk of radius 1 plus epsilon.
It's better to write it just in terms of conditions on the growth of the coefficients, then it's easier to see.
Yeah, so I mean, that's probably a better thing to do. Yeah, I think that's better than writing it in terms of this, because this is a nuclear Fauché space. That's not going to make it easier. So yeah, the set of coefficients Cn such that the sum of Cn r to the n is less than infinity. And we can view this, for example, as a Banach space. So I should say 1 plus epsilon. Oh, a Banach space with respect to the Banach norm given by this this expression here. But you know, it's going to be for reasons similar to the discussion of trace class maps. It's not going to really matter the specifics of the topology on this space, because when you increase epsilon, so it's a sequence space. When you decrease epsilon, the transition maps are given by this rapidly decaying, well, not rapidly, but yeah, kind of a multiplication by diagonal matrix, kind of a, yeah, what can I call it? Yeah, t squared, t cubed. So whatever you have to do to make r turn into, or to make 1 plus epsilon turn into 1 plus epsilon prime, yeah, for a smaller epsilon. So but you're multiplying by some decreasing sequence, and these sequences which decrease like powers of something, they're always p summable for any p. They grow, yeah. So this will be these transition maps are a basic example of a trace class map. And you can see that, yeah, actually, I mean, you can check using, I mean, you might wonder, is this a priori the correct description of the topology on the ring of holomorphic functions? But you can check, I mean, this Cauchy integral formula for, you know, relating the values of a holomorphic function or the values of a derivative and so on to the Taylor coefficients will make a comparison between these things very easy. And in fact, it's very difficult to write down the wrong topology on a space of holomorphic functions. Okay. Right. So that's a basic example of a dual nuclear Fauché space. And when you do the calculations, for example, using exactly this inductive system, you find that if you take holomorphic functions on D and tensor it with itself, say, and well, maybe I'll call it the D1 and D2. This is a holomorphic functions on D1 cross D2 bar. So this is a holomorphic functions on the two-dimensional polydisk. And again, it is the easiest thing to do is always just read it in terms of convergence properties of the associated power series. Okay. Now I want to extract some corollaries from this relating to holomorphic functions. So now let's take D and D prime, two closed disks in the complex plane. Then let's say contained in a bigger disk. Let's call it E bar. Then you can take the derived liquid tensor product over OE bar of OD bar with O of D prime bar. And this is just going to be concentrated in degree 0, and it'll be the holomorphic functions on the intersection of the two disks. So let me give the proof or the little argument, I guess. So first, actually, we're going to use a somewhat analogous trick to what Peter used in producing the liquid theory. So a priori, if you wanted to understand this derived tensor product, you'd have to write it as a, you know, geometric real, or you'd have to resolve it as a, you know, a geometric realization of absolute tensor products of all of these various, you know, copies of these things, right? This usual bar construction, and those would all be dual nuclear Fauché spaces, and you can analyze the tensor product, and everything is okay. Still, it's kind of you have to prove it's concentrated in degree 0. You'd have to prove exactness of this complex, and it'd be maybe kind of annoying. But we can use this trick of replacing this with just something purely algebraic. So the polynomial functions on the complex plane, so C bracket T. Yeah, Scholze, it depends what you mean by nuclear space. So if you mean either dual nuclear Frechet or nuclear Frechet, then yeah, I think I agree with Peter. But if you mean a general nuclear space in the sense, well, that I guess I haven't discussed in this lecture yet, then I guess the answer is probably no. Yeah, so first replace this with this. And the advantage of that is, well, then this, yeah. So this is just, well, this is just the underived tensor product. I mean, sorry, it's just, well, this is, yeah. Yeah, by the way, when I was doing these calculations, all these calculations with dual nuclear Frechet spaces and so on, part of the claim is that the derived tensor product is concentrated in degree 0. So it just comes out of the calculation because you know that's happening on the compact projectives, and then you have the sequential colimit. So, right. And then you have to set sort of T1 equals T2 in some sense. So this is just pure algebraic nonsense. So action of T here has to be equal, and this should be derived modding out, okay, but it's not going to matter. And then this is O of D hat cross D prime hat, T1 minus T2. And then it's just some fairly classical analysis of rings of holomorphic functions that in this case is the same thing as the functions on the intersection. Okay, so that works for doing it over this algebraic base, but now let's note a special case. So if you take, say, any disk, for example, E bar, and then you tensor it over a CT, a derived tensor product, OE bar, this is just OE bar again. So that, yeah, that's just a special case of what I just showed, but where D and D prime are equal to this EE bar. And that implies that the tensor product over derived tensor over OE bar is the same as CT. And then that implies the claim. So that's all, yeah. Well, that kind of trick is useful also for calculations. Okay, so that was, so, well, the moral of the story here, by the way, yeah. So a special case, if D and D prime don't intersect, then the tensor product of these rings is 0. I'll just keep that in mind. So the moral of the story here is that the algebra reflects the topology of the complex numbers. So the algebra of holomorphic functions. So when you can do these tensor product calculations for rings of holomorphic functions, it's just intersections on the level of the topological space, the complex numbers. And that's going to be important for what we do in the second half. Right. Have we used the liquid theory somewhere now? Yes. I mean, the liquid theory is what is making these tensor products well-defined, these tensor products that we're calculating.
But didn't you say that all these spaces are nuclear Frechet? And then you already had the
Oh yeah, you could do all these calculations in the classical context as well. Yeah, so the power of having good derived categories and so on is going to be more evident in the second half. But actually already, maybe, yeah, so let me explain where we're going. And then maybe I can make a remark which will help indicate why it's good to have the liquid theory and not work in the classical context. So where are we going? So there's this, well, this extremely, we want to reprove 2 classical theorems. So let X be a compact Riemann surface. And E a holomorphic vector bundle. Then yeah, well, oops, HI is a finite dimensional vector space for all I, and I'd say it's 0 for I big enough, but in fact, well, we'll see very shortly that I bigger, bigger than or equal to 2 is going to be sufficient. And the second thing is that if you take H0 of XE, this is in duality with H1 of X with E. With H1 of X with coefficients in the vector bundle of one forms tensor the dual. So these are these classic theorems about Riemann surface, and the proofs generally tend to use functional analysis. So we thought this would be a good place to see how things look from the liquid perspective. So how we'll prove it? We'll produce a theory of quasi-coherent sheaves. On the Riemann surface or complex, a compact complex manifold, or Riemann surfaces, equipped with a 6-functor formalism, which means basically that you can makes it easy to prove duality statements locally. That's what I guess that's a main thing that 6-functor formalisms are good for, is to reduce duality statements to local calculations. So that is more or less how we're going to be able to get to. Do you need to restrict to compact? No, not really, Arthur. But the statement is you have to be a little careful how you state it in the non-compact case. So I'll probably only get into that when I'm talking about the proof. Yeah.
I mean, definitely the statements as stated, they can only be true if it's compact.
Yes. With this statement, it's definitely only true in the compact case, but I'm sure Arthur knows that quite well. The theory of quasi-coherent sheaves in the 6-functor formalism, no, that you don't need to restrict to compact there. That's one of the points, yeah. So it lets you work locally, and locally you're not a compact manifold. But maybe I'll say a word already about. So I want to indicate how the liquid formalism is going to help with this. Well, maybe I'll say one word about this. Where one will come from. One will come from. Perfect complexes over the complex numbers, and to emphasize that it's purely algebraic, I'll put C evaluated at the base point. So just the underlying discrete ring is the same thing as nuclear liquid modules. I don't need the P really. Intersect compact liquid P modules. So what we'll really see is that the derived global sections of a vector bundle is both a nuclear space and a compact object in the liquid theory. And then here I can explain what happens when it's non-compact. So when it's non-compact, there's two different kinds of global sections you might consider. There's ordinary global sections and compactly supported global sections. And the story is going to be that, well, at least if the Riemann surface is sigma compact, then the ordinary global sections are always going to be nuclear, and the compactly supported global sections are, now I need to be careful. The compactly supported global sections, wait, is this true?
Can't quite be right, but
it's very close to being correct. I was
you
going
do
to
it
say they're
on-
always compact, but that's not really true. Anyway,
Well, if you evaluate on a closed disk or something, they will be compact.
yeah.
I guess.
Well, anyway, as a heuristic, yeah, the idea is that there are actually two different functors in general: the compactly supported cohomology and ordinary cohomology. One has one property, the other has the other, and the compact case is when they coincide, and then you're in the intersection, which will mean you're a perfect complex. And so I'll explain why this intersection claim is true when we get there. And as for two will come from the six-functor formalism, meaning we can work locally. But here I want to make a caution, and this will also relate to another use of why it's important to have this liquid framework or some other similar framework, I'll say, because it's true. You could imagine other possible frameworks where you can run this sort of argument, but at the very least, a theory of quasi-coherent sheaves on complex manifolds or complex analytic spaces has to be derived. So there can only be a good derived category of quasi-coherent sheaves. There will be no T structure. There will be no abelian category. And the reason is very easy to explain. Actually, it follows from what I've already said. So if you can take a big disk E and then a little disk D and then a disjoint little disk D prime. The reason is going to be basically is that the base change map, no matter what formalism you have, as long as it does what you want it to do, then the base change map is not going to be flat, is not going to be exact. So this O of D will not be flat as an O of E module, provided the formalism behaves the way you'd like it to. And the proof of this is that, let's take this to be the co-kernel of the following injection. So O of E mapping to O of D prime, D prime. Right. So first of all, O of E, this is an injection, right? So a holomorphic function on E is determined by its restriction to D prime by the identity principle for holomorphic functions. So this is an example of one of these non-Hausdorff quotients. But they have those kind of things so it's a weird object, but those kinds of things have to be there if you're going to have an abelian category. So that also has to be there. If tensor product, but when we tensor up to O of D, then we'll get, but if we apply this operation, then we're getting this inclusion, so O of E including into O of D prime, this becomes O of, so O of E tensor O of E with anything is, why am I getting so confused about this? This is completely elementary. So this becomes O of D mapping to, and then, but then we do the relative tensor product OD prime tensor OD over OE. Those are disjoint disks, so we get 0. Yeah. Maybe I wasn't supposed to take the co-kernel. I mean, I just want to apply it to this inclusion. Yeah. Okay. If it's not, for it not to be flat, I should give you an inclusion that doesn't go to an inclusion. So this inclusion goes to the 0 map, and therefore the base change cannot be flat. Right. I mean, the base change map is not exact. So there can be no global abelian category, but this does not obstruct there being a global derived category. And in fact, there is going to be a good global derived category of quasi-coherent sheaves. And you shouldn't be too scared by this, because in this situation, there's a Tor 1 against this guy, this co-kernel here, but no higher Tors. And so the situation is still very much under control, and you can still calculate everything. It's just a fact of life that the T structure gets messed up when you localize. so that you don't have a global abelian category. It's not the end of the world. It's just a remark you have to take into account. Okay. So how are we going to do this? So let me also remark that, so in Peter's notes, well, I guess, yeah, we also produced a 6-functor formalism for coherent cohomology. Well, I mean, for here, it's the same thing, okay? For coherent cohomology in algebraic geometry. So you can CF Peter's notes condensed.pdf. And that got generalized to well, in some sense, the kind of discussion that happened in building so the 6-functor formalism and new kind of solid quasi-coherent sheaves. And that got generalized to this idea of analytic spaces. And a new idea of open subset, which was called steady localization. So that even for a familiar thing like a scheme, you a priori have a new underlying topological space with a lot more opens possibly, and a theory of quasi-coherent sheaves where you can still descend along such opens. And you could try to use that formalism to talk about quasi-coherent sheaves in complex analytic spaces, and produce a 6-functor formalism there. That would be fine. But I'm gonna but I'll take a half classical in this lecture. I'll take a half classical approach. So I'll use the underlying topological space. Use the usual underlying topological space. And just put a sheaf of condensed rings on it. And then the quasi-coherent sheaves will be certain kind of condensed modules over that condensed ring. Right. Yeah, so it's half classical in the sense that the topological space is going to be classical, but the structure sheaf is going to be, condensed, in fact, liquid. Whereas in this frame kind of stuff that Peter talks in his notes, both the topological space and the structure sheaf, so to speak, are kind of new sorts of objects. But this also gives me an excuse. So in fact, so it actually will build on the original 6-functor formalism. So for derived categories of sheaves of abelian groups on X, a finite dimensional locally compact Hausdorff space. So this is now just sheaves of ordinary discrete Z modules. We're forgetting about condensed stuff just for a little while to, I want to take some time and give a little pedagogical introduction to 6-functor formalisms, focusing on the original in quotation marks case, or the sort of simplest case in which you have a 6-functor formalism, which is usual sheaves on usual locally compact Hausdorff spaces. And I put original in quotation marks because actually the original setting was a tall sheaves in algebraic geometry, but that's kind of a historical accident because that's what Grothendieck was thinking about when he invented the concept of 6-functor formalism. In Biorites, the first one should have been the much simpler one of usual topological spaces, but it was Grothendieck happened to think about the other thing, so that's where it got done first. And he said his student Verdier to develop what I'm going to describe here, I believe, is how it went. So I'm going to start with some reminders on derived categories of sheaves, or reminders, or if you don't know, it will be an introduction. So yeah, for me, for this section, X is always going to be a finite dimensional locally compact Hausdorff space. So, well, it's an abelian category, this category of sheaves of Z modules. So we can take its derived category. And since we're now all very modern people, there's something else we can do, which is take sheaves in sort of Jacob Lurie's sense on the topological space with values in the infinity category, derived category of Z. Under the hypotheses that I've set forth, these are actually the same thing. And it's also the same thing as whatever variance you like. Yeah, everything is automatically hypercomplete or Postnikov complete or whatever you want. And all of this is due to this assumption of finite dimensionality, and well, locally compact Hausdorff spaces are about as nice as you want. And so you can, so then there will be two perspectives on everything we do. If you're trying to produce some operations on the derived category, there's kind of two ways to do it. You take the classical thing on abelian categories and derive it, or two, directly define the derived thing as the derived analog of classical thing. So I'll give a couple of examples later. So there's some classical operations on sheaves, like the push forward and the compactly supported push forward and things like this. You could either take their derived functors and use that to define some derived push forward and derived compactly supported push forward, or you could just look at the definition of the thing and try to guess what the derived analog would be and take that as your definition, sort of in this perspective here. And for me, I find the second approach to be much more illuminating, because whenever you do the first approach, you always have to implicitly injectively resolve your sheaves or something like this, and that's just and then you lose all track of what anything means when you do that. You depart from all kinds of geometric or topological intuition. Whereas in fact, when you just directly define the derived analog, then you can actually understand what's going on. So let me right. So we'll take this one here. So what are the important operations you have on categories of sheaves? Well, so if you have almost out of, okay, I'll give the most basic one, yeah? So if we have a function from f to y, then we get a pullback functor oh, there's another reason, by the way. Oh, shoot. There's another reason to take approach 2, which is we're eventually going to do sheaves on X with values in like liquid modules or something like this. Well, liquid modules don't have enough injectives because of this set theoretic nonsense. And on the other hand, you can't use projectives to derive functors on sheaf categories on ordinary topological spaces. So we would actually have a little bit of trouble defining things a priori if we stuck to the original perspective. But if you always think in these terms, then there's no problem whatsoever. Right. So I have a pullback functor here, and it has a right adjoint f lower star. And actually, the right adjoint is kind of easier to write a formula for. So if you take the right adjoint f and evaluate it on V subset y, this is just the same thing as f evaluated on the preimage of V, which is now a subset of X. So that's the classical description of the push forward, and it also works as the description of the derived push forward. And classically, the pullback of f is, well, it's the left adjoint. And you define it as you do some pre-sheaf thing and then sheafify it, so that you do some more or less evident pre-sheaf thing as some filtered colimit of neighborhoods, which are pulled back from the base. And then you take the sheafification of that, and it's the same thing in the derived world. So it's just what it has to be as an adjoint. And in some sense, this one's more fundamental. So this one, it looks like it's inexplicit in terms of its values on open subsets, and it is. But the nice thing about it is that pullback commutes with stocks. And actually, Peter already mentioned this when he was in his very first lecture. So if you take the pullback of F and you take the stock at an X, it's the same thing as stock at the image of X, where this is, as usual, the filtered colimit over all open neighborhoods of Y and Y of the sections over that neighborhood. So you get control over both the push forward and the pullback kind of in this way. Right, and again, this is the usual classical definition, and you can just take the derived analog, so the filtered colimit in the infinity category, and it gives the correct thing. Okay, so I realize I'll pick up this story after the break.